Hi, everybody. Welcome to this session of DOTS and the start of a new season. We're happy to start today with Dr. Cathy Wu, who is an associate professor at MIT in um, LIDS, CE, and IDSS. She holds a PhD from UC Berkeley, bachelor's and master's from MIT, all in ECS, and completed a postdoc at Microsoft Research. Her research advances machine learning for control and optimization in mobility. She is broadly interested in AI for engineering. Cathy has received a number of awards, including the NSF Career Award, PhD dissertation awards, and publications with distinction. She serves on the board of governors for IEEE ITSS, is a program co-chair for RLC 2025, and is an associate editor or equivalent for ICML, NeurIPS, and ICRA. She is also spearheading efforts towards reproducible research in transportation, including co-founding the Rewrite working group. And I'm sure she'd be very happy to talk about all these other things that she's working on as well during breakout rooms in more detail. So we are very happy to have you here, Cathy. You have about 25, 28 minutes. It's all yours.
Thanks so much for the invitation. I'm really excited to be part of this seminar series and to share what we've been up to, what myself and my students have been doing. And I will just say that I did a bit of a double take when I first got the invitation because of the acronym DOT, because I work in mobility or transportation. DOT to me stands for Department of Transportation. So it's sort of doubly appropriate that I'm speaking in this session, speaking about discrete optimization, but in the context of mobility. So I'll be talking about learning guided optimization. I'll sort of break down what this means. But first, I'd like to start with the sort of 20,000 foot view of what I am trying to do. And I would characterize this as something like AI for systems modeling. Systems modeling is a core part of the engineering process for, say, designing future transportation systems, other systems as well, power systems, water networks, and complex engineering systems. So let's start with the classical paradigm, which is conducted in various forms of systems engineering, which is where you take a problem of interest and you really try to simplify it and cast it into a model-based framework. You can take your favorite one. It can be, say, your mixed integer linear programming framework, your model predictive control framework. I think about both control and optimization problems, so I'm just giving you an example of each. Then you would solve the problem using your model-based solver. You analyze the result, and because you simplify the problem, oftentimes this is an iterative process of reintroducing complexity into the model, and sometimes that can be very difficult. So if I were to put time complexity, like not time complexity, actual times spent on these different stages, I would say, well, maybe it takes a few weeks to cast the problem into a model-based framework. This is not counting the time it takes for, say, a student to like take a course on the model-based framework itself. Typically, solving is not the difficult part. Maybe it takes an hour, maybe a day. The really difficult part often comes in reintroducing the complexity. I mean, you simplify the problem to fit into a model-based framework to begin with, so those simplifications may lose out on some important characteristics you really want to capture, but the model-based frameworks have limitations. So I first came across this in grad school when I was working with traffic control problems, and I realized that it's still quite hard to both jointly consider the nonlinear dynamics in traffic flow in conjunction with discrete decisions like lane changing. Lane changing is very common. It's quite common also to just simplify my network into a single lane road, so I have no lane changes. But now there are gaps in my analysis. If I were to solve this using a model-based solver, it's not clear how applicable my analysis is to the system that I actually care about. So I became very interested in the wake of sort of the deep reinforcement learning, so the rise of these techniques. And it led me to really consider an emerging paradigm, which we might call AI-assisted system modeling. So the components are more or less the same, but now when we simplify the problem, we can cast it into a more model-free framework. So this is like a simulator. You just need your inputs and outputs. You can encode the logic that you're interested in, you don't necessarily need to conform it to an explicit model-based framework. So um, in terms of time, this might take a little bit less time. Maybe solving takes a bit more time, but the real gain is in the reintroducing of complexity. Of course, we typically still simplify the problem for the sake of analysis and incremental engineering. But then when we reintroduce the complexity, now it's a matter of coding up the logic that we didn't include in the previous iteration, and this can take on the order of days rather than, say, years. So this, I think, would be game changing if we were able to do this. And this is what I've been trying to do and probably will continue trying to do for many years to come. As a note, now that we're in the age of large language models and ChatGPT, there's another gain that we could consider, which is not the focus of the discussion, but just to connect the dots here. Modeling can be even easier. I might just tell the system, now I want to consider lane changes, and in a couple of minutes, I could update my model to include the complexity that I did not previously consider. Okay, so I might even be able to drill down from days to minutes. So let me now make this more explicit with an example from the engineering context and in particular from mobility. So let me use the example of vehicle routing problems, a classic discrete optimization problem. And if you're not familiar with this problem, just imagine Amazon's package delivery problem. There are millions of packages to be delivered in a major metropolitan area, like here in Boston. And Amazon must determine which package goes on which truck to go to which, customer location. And I like to bring this up because the vehicle routing problem is not one precise specific problem, but rather a family of problems. Here's a schematic from a recent survey that depicts this quite nicely. We have the vehicle routing problem here. Our vehicle routing problem might have various constraints, various terms in the objective, various, types of distributions. So, for example, it's very common to consider a fleet of vehicles with a certain capacity, like your trucks do have finite storage space. In some other cases, you might need to pick up before dropping off. For instance, in the taxi case, there may be some notion of deadlines or time windows. For instance, food delivery. There may be some sort of time constraints. There are so many of these different variations. In recent years, we're interested in electrification, so there may be charging constraints to consider as well. So this is, vehicle routing problems are a generalization of the traveling salesman problem. This is a family of NP-hard problems. And these different constraints that I just rattled off, that constitutes another complexity. So you can view this as a combinatorial family of combinatorial problems. You can have any combination of those constraints, which forms a new vehicle routing problem variant. And that's not the only ones. There's maybe dozens, if not hundreds, of these different constraints. So it is fairly intractable to solve these one by one in a manual manner where we devise custom algorithms for these different variants. And to give you a sense of this, this is a timeline of the historical solver development for vehicle routing problems. I went back about 20 years. So starting with Concord, which is a state-of-the-art solver for TSP. So this is the one vehicle setting. And one way to view this progression is that while we are improving the performance and we are enriching the solvers, we are, in some sense, it has taken us 20 years to incorporate the constraint on the problem that now we can have multiple vehicles. Okay, and it's still a very active field of research to continue to incorporate additional constraints, the time window constraints, the capacity constraints, the pickup and delivery constraints, and combinations thereof. So this solver development is following that classic paradigm of as the world evolves and as we are interested in different constraints, different versions of the problem, we currently take years to iterate on improving our model-based paradigms. And this is done, more or less manually. So again, this is where the interest comes in terms of, well, to what extent can, our modern AI tools assist with this process? To what extent can we automatically derive algorithms for novel variants of the vehicle routing problem? So I see this arise in various domains within mobility. And it really stems from various aspects of system complexity. So I see this in traffic, autonomous mobility, autonomous warehousing, mass transit, supply chain and logistics. And I'll sort of skip this, but the sources of complexity vary from application to application, but they more or less give rise to the same challenge, that there are variants of the same problem that are hard for that's hard for the current paradigm to handle. So the bottom line is that there are countless variants of optimization and control problems. It's intractable for us to manually design solutions for each of these. So to what extent can machine learning help? So this is a short talk, so I unfortunately will have to breeze through many details, but what I hope to do is give you a high-level sense of the general approach and give you a flavor of what we do. And then, of course, I'm happy to discuss more in the breakout or offline. So here's a cartoon of the optimization landscape, solver landscape. On the x-axis, we have how much work does it take to design a solver for a new problem variant. Let's consider just like one class, so like vehicle routing as one class, or warehouse automation as one class. We're not trying to solve, all of the world's problems in this line of work. But ideally, we would like to be able to adapt to a new problem variant with fairly low effort. And we would like our solver to be effective. I'm lumping together performance and speed. So this is the yellow star. And in general, there are three approaches. One is an end-to-end learning approach. So for instance, using deep reinforcement learning, these tend to be, unfortunately, the least effective of the three types of solvers that I'll talk about. The second are our classic model-based solvers. It's a bit more effort in the sense that you have to take a class, you have to, you have to learn the language, you have to conform the problem, and they're, more effective. The most effective methods that in my experience and what I've seen in speaking with a lot of practitioners, is that there are specialized heuristic methods for different problems, and these are highly manual. These are highly tailored to specific settings. If the setting were to change, you need to tailor it again. So what my research group studies is a couple problems in this space. So one of which is part of the challenge, I believe, to having more effective end-to-end solvers is that deep reinforcement learning remains quite sensitive to various aspects of the training. And so we are working on improving training reliability. This is fairly generic. This is less specific to discrete optimization, so I won't be focusing on it today. What I'll focus on today is this other line of work, which is about hybridizing learning and existing solvers that are already at some level of effectiveness and understanding how we can achieve the best of both worlds. Okay. And a third line of work, which is complementary to these, is applying these techniques to increasingly challenging mobility problems as we innovate on the methods. Okay, so again, I'll be focusing on this line of work today. So the approach that we've primarily taken in recent years in terms of hybridizing learning and search is learning guided optimization, which is also the title of this talk. So let me contrast this with the optimization only approach, which is where we have a problem instance, we feed it into a solver, and we get some solution. Now, if we take a closer look at this solver, it's got a jumble of components. And let me label these components as some being structural and some being non-structural. These are loose terms, and what I mean by structural are those that are required to preserve the original properties of the solver. So for instance, any kind of guarantees. And our perspective on learning guided optimization in recent years is that, let's not touch the structural elements. So let's not like, have the house collapse under a broken foundation. Let's actually focus on the non-structural elements. And this is where we can incorporate learning, like deep neural networks, and what we can do is we can, I guess one thing I forgot to say a bit earlier is one of the limitations of this classical paradigm is that we could feed the same problem instance to the solver day in and day out, and the solver does not get any smarter. It doesn't know that it could just, give the same solution that it gave yesterday, with the, exception of warm starting. So, we could potentially do much better if we have some either historical data set of representative instances, synthetic instances that are representative in some way. And so that leads us to this picture, where this deep neural network, which affects, the solve time, can be pre-trained in an offline manner using a distribution of instances. Then during inference time, again, we feed in a problem instance, and now the solver can incorporate the historical knowledge and actually improve its solution quality or solve time. So this is the paradigm that we've been exploring over the last few years. A few questions that we would be interested in, or in other words, a few pros and cons, are, well, with this approach, you can only do better because if you do worse, you can always reset to the original component. But how much better can you do? And this can be fairly general because you can always decompose a solver into, elements you should touch, elements you shouldn't touch. But how general is this? And also I think a fundamental limitation of this approach is that we will be limited by, say, the structural elements of the solver, the elements that we don't touch. So if those take a while to solve, then, we're sort of bound by that kind of solve time. So, again, I'll be relatively quick, but I do want to give you a flavor of what this looks like in a with a concrete project. So this is a paper that was published at NeurIPS in 2023 titled Learning to Configure Separators in Branch and Cut. And this is an example of learning guided optimization in the context of mixed integer linear programming. So I think I don't need to preach to the choir here, but mixed integer linear programs are everywhere. And there are standard solvers for these, including Gurobi, Cplex, and in our case, we use Skip to do most of our research development because it's an open source solver. So what's important to note is that even though Skip and these mixed integer linear program solvers provide guarantees, there are actually a number of heuristic components that actually are responsible for the fast solve time of these problems. So there are, great elements, branch and cut, everything's great, but there are a number of bells and whistles to make the solvers actually practical, including primal heuristics, and just even heuristics within branching, heuristics within cutting. So this has led to a lot of interest in learning for branch and cut. And so there's a bunch of prior work on algorithm configuration, learning to branch, learning to cut. You can think of these solvers as, broadly speaking, splitting into a branching component and splitting into a cutting component. Our observation a few years ago is that there's an element when we profile the solver. A lot of the solve time actually goes to this, less discussed component, which is called cut generation or separator configuration. So, so often in these solvers, there's a lot of interest in, say, how do we branch intelligently? Also, how do we select a cut from a cut pool intelligently? What we're addressing is, okay, where do these cuts come from in the first place? It turns out that a lot of time in the solver is spent invoking a set of algorithms like Gomery, Clique, and so on to generate cuts into this cut pool. Now, if you generate cuts but they're never selected, that was a waste of time. So that's an insight that led to this work. So we introduced a new task to the machine learning community, which is the separator configuration task. So which separators or cutting plane algorithms should we actually invoke for a specific problem instance to, achieve the best solve time or the best solution quality? So now being very quick, the key challenge of this work is that there are something like 20 separators or cutting plane algorithms. And so the action space is actually 2 to the 20 because we generate cuts into the cut pool from a combination of these cutting plane algorithms. It's not just selecting one. So that is the major challenge of this work. How do you handle this large action space? Okay, so this large configuration space. So one aspect that's a little clever about our work is this key idea of diminishing marginal returns, or in other words, submodularity, if you're familiar with that concept. So at a high level, if we have the set of all configurations denoted by this red A, okay, the optimal predictor performance is going to be submodular in the set of configurations that we actually consider. In other words, the more configurations that we consider, we're going to experience marginal diminishing returns. The wonderful thing about submodularity is that if it's true, then you can you can greedily construct an approximate solution that is quite strong in a greedy manner. So that's what we're able to do. So we greedily construct a subset, this A bar, okay, that's much smaller than the original set. So recall that the set A is something like 2 to the 20. And in practice, our restricted set is going to be around 20. This is much more tractable. It's very difficult for a learning algorithm to learn to choose between 2 to the 20 different options, much more tractable to choose between 20. So this is the overall schematic of our algorithm. We have this unrestricted action space, which we restrict to about 20 actions. Then this is where the learning part comes in. We have an instance-aware predictor that takes in the problem instance itself and then outputs which of those 20 separator configurations to actually invoke during inference time. This is trained in a contextual bandit manner, and overall, this algorithm is titled Learn to Separate. So in order to have a neural network, or in order to take a neural network, a deep learning approach, we need to encode the mixed integer linear program itself. So this means the A, B, C matrices, as well as which variables are integral. And so this is fairly standard, but we did need to modify um, the architecture to incorporate the separator component. So here we have a graph neural network that encodes the variables, encodes the constraints, encodes the separators with appropriate weights in between. There's a number of node level or edge level features that we include. I know it's small, details are in the paper if you're interested. I just mean to indicate that there is information that's encoded into this graph, including some hand design features. Then this is the input encoding. Then we pass this through a graph neural network that outputs either the solve time or the solution cost, depending on our experimental setup. So we have two sets of experiments. One is where we hold the solve time constant and we try to improve the solution quality. The other is where we fix the gap and we try to improve the solve time. So let's jump to the results. This is an example of, this is sort of a good case. Here we have the default skip, and these are the primal and dual bounds as a function of the solve time. And what you can see is that under the learn to separate model, we can accelerate actually both the primal and dual. So where does the benefit come from? Of course, it comes from reducing the time to generate the cut pool. But what's also interesting is that when we measure the time spent in other components of the solver, those are actually also decreased. So we infer that this is because by generating a higher quality cut pool, more effective cuts are selected, which means that there can be less time spent, a smaller depth of tree, and so on and so forth. Okay, so there is sort of primary effects and secondary effects that both contribute to reducing the solve time. So jumping now to the results, here we consider a number of canonical benchmarks from the Tang paper, from the Eckel paper. These are classic problems like bin packing and facility location. Here's the default solve time, and we report a performance improvement relative to this. So default is at 0. And what we see is relative time improvements of between 30 and 70%. This is for skip. We also benchmark this for Gurobi. We see similar values, but I will note that because Gurobi is closed source, there's a little less control we have over the stages of decision making. We also benchmark real-world benchmarks, including MIPLib, neural network verification, and load balancing. And of course, these problems are going to be more challenging. But we still see improvements of 10 to 40%. And I would say I would view this work as a prototype. We're being very modest in terms of compute. So, one GPU that's, 3 generations old. This is a single task training, one MILP class per model. Where the data set is extremely small, about 100 instances for restricting the configuration space, and then about 800 instances for training. We train for about 2 days. Our evaluation is over about 100 instances. So I will now just sort of jump over to give a flavor of a few follow-on works. So these days we're very interested in foundation models. By we, I mean the community. And one of the limitations for MILPs is the data shortage. So we basically have we have data sets that are either many classes, but few instances, like MIPLib is many classes, but few instances. Or we have synthetic instance generators where we can have as many instances as we want, but very few classes. So an idea that we had, which this is a very recent paper that will appear at iClear, is that we could use large language models to generate more instance generators. So we can actually take the code that generates, this infinite data, and we can evolve them to provide novel classes of MILPs. And what we show is that if we then train on various MILP tasks over the data generated from this versus from this, we can actually improve on the solution quality quite a bit. So I have more to share as always. And so here's a sort of snapshot of some of the other works we've been able to work on: large vehicle routing problems, large multi-agent coordination problems in robotic warehouses. I talked about these mill problems. We've worked on long horizon optimization problems. And the TLDR, I think, of what we're doing is we're in some sense taking these classical solvers and we're finding a way to pre-train them so that they can operate better and faster during inference time. Thank you very much.
Um, Thank you, Kathy. I think that we probably should save questions for the breakout room just because we're hitting the half an hour mark, counting the introduction. But please stick around for the breakout rooms and after Manisha's talk, if you'd like to talk to Kathy and discuss things. Thank you very much for the fantastic talk.